Hello from Chem Help ASAP. This video provides practice for determining the hybridization, bond angle, and geometry of second-row atoms in organic molecules. Check the video description to find links to printable copies of these problems and their solutions. There will be links during the video that will connect you to other relevant tutorial videos that you might find helpful. I promise we'll get to the question soon, but hybridization is a bit of a controversial topic, and I feel I need to give some framing for these problems. In the early days of organic chemistry, chemists wanted a simple method for estimating bond angles and geometries of atoms. Determining an atom's hybridization allows these predictions. Determining hybridization is very easy and quick, and the bond angle and geometry predictions are reasonably accurate. Hybridization can even be used to understand an atom's reactivity in some cases. Hybridization is limited mostly to second-row elements. However, many people use hybridization in discussions of larger atoms. So follow the lead of your chemistry instructor. Always follow your instructor's lead because your instructor is the one who is evaluating you. If I say anything in this video that conflicts with your instructor, then please let me know in the comments and I'm sure we can resolve the difference. So how do you determine the hybridization of an atom? We'll go through this process stepwise. It's very easy. Once you apply these rules, even just a few times, they will become second nature. First step, does the atom in question have more than one attached atom? In other words, is the atom in question attached to two or more atoms? If no, then the atom in question does not have a bond angle or geometry. So hybridization is meaningless. Note, you can still go through these steps regardless of whether the answer to this question is yes or no. In fact, I will do so in some of our problems. I just want to leave this question here in case your instructor has a more strict view of hybridization. Second step, how many atoms are attached to the atom in question? This is the number of attached atoms, not the number of bonds. This value is A. Third step, how many lone pairs are on the atom in question? This value is L. Fourth step, is the atom in question attached to a pi bond? And does the atom have at least one lone pair? So L has to be greater than 0. If the answer to both these questions is yes, then P equals 1. Otherwise, P equals 0. This fourth step may cause some questions, and you don't normally see it in many textbooks. This step is important for proper accommodation of an idea called resonance. Which most students won't encounter in high school or even in college general chemistry. Fifth step, add A to L and subtract P to calculate the number of hybrids you need on your atom. This value is H. Finally, use the chart in the lower right. If H is 4, then the atom is sp3 hybridized. If H is 3, then sp2. If H is 2, then sp. Does this process work? Absolutely. Is it possible to find an atom that doesn't work well with this method? Absolutely. The exceptions, however, are almost exclusively part of highly unstable and uncommon structures. The steps on this slide are very, very reliable. That was hybridization. Now how do we determine bond angles and geometries? Well, we can now use our hybridization, the rows on this table, with the attached atoms, A from the previous slide as the columns, to predict the bond angles and geometries from this table. We won't go through this table now, but we will refer back to it a few times as we work the problems, especially the early ones. Let's get started. Here's our first question. This is ethanol, and we have 3 second-row atoms. So let's focus in on those. Let's do this carbon first. And let's just work through our questions. I tried to put our questions up here in the corner. I hope that's large enough for you to see, but I also didn't want to get in the way. So the first question, do we have on this carbon more than one attached atom? Well, yes, we have 4 attached atoms. So that clears that hurdle. So question 2, how many attached atoms do we have? Well, of course, we have 4. 1, 2, 3, 4. Therefore, A equals 4. Step 3, do we have any lone pairs? Nope. 0 lone pairs, so that's 0. So question 4 is, do we have a pi bond and is L greater than 0? Well, we don't have any lone pairs, so P is not equal to 1, P equals 0. So let's go to our equation. H equals A plus L, that's 4. Well, 4 plus 0 minus 0, so H equals 4. Therefore, if H equals 4, that's how many hybrids we need, and this is going to be sp3 hybridized. Great, so this is sp3 hybridized. Now, let's remember our values here. sp3 hybridized and A equals 4, and let's go back to that other table. Here is our table. We have an sp3 hybridized atom with 4 attached atoms. Therefore, our bond angle is approximately 109.5 and the geometry is tetrahedral. So let's just write this in. We are 109.5 and we are tetrahedral. Now, it won't be exactly 109.5, but all sp3 atoms have bond angles that are approximately 109.5. Okay, let's go to the next carbon. Now, I'm going to make this one a little shorter because it's very similar to the one we just did. We have a carbon which is certainly attached to more than one atom, so that clears the first question. The number of attached atoms is, again, 4. 1, 2, 3, 4. So A equals 4. We have no lone pairs. Since we don't have any lone pairs, question 4 is kind of moot. So the P equals 0, and that gives us, again, H equals A, that's 4, plus 0 minus 0, so H equals 4. And if we need 4 hybrids, we are going to be sp3 hybridized. Now, we don't need to look at the table here because, again, we have sp3 hybridized and I'm sorry, not H, but A equals 4 and sp3 hybridized. And that's exactly what we had last time. So we are, again, going to get the bond angle is about 109.5, and this is a tetrahedral atom. Fantastic. Okay, we're making headway. Let's do this oxygen. This oxygen has at least 2 attached atoms. There's the oxygen, 1, 2. So we're fine on question 1. Question 2, we just counted those atoms. We have 2 attached atoms. We actually have lone pairs for this oxygen. We have 2 lone pairs. Note that we're counting the lone pairs, not the total number of electrons. That's just 2 lone pairs. Do we have a neighboring pi bond? No, we don't. We do have lone pairs, but no neighboring pi bond. So P is not equal to 1. P is going to be equal to 0. Now we go to our equation. H equals A, which is 2, plus P, A, which is 2, plus L, which is 2, minus P, which is 0, and that gives us 4. And so if it's 4, we are sp3 hybridized. Now, this is a little different. We're going to go back to this table because, again, we have sp3, but our value for A is different. So let's go back to this table. Here we are on our table. We are sp3 hybridized. We have 2 attached atoms. The value for A is 2, so that means we're 109.5, kind of, and bent. So let's go back to our page. We are going to have a bond angle of 109.5, and this is bent. Now, you may know from your class that, the bond angle here really isn't exactly 109.5. This is probably more like water, and maybe it's more like about 104.5. But it's pretty close to 109.5. Me personally, I consider those about the same number. Your instructor may want you to know exactly what water is, and this is more water-like. But it's approximately 109.5. Okay, so that's the first problem. Let's go to the next problem. All right, problem number 2. We have 3 second row elements in this problem as well, so let's get to work on these. Here we have this carbon. This carbon is certainly attached to more than one atom, so it clears the first hurdle. Question number 2, the number of attached atoms, we just circled them. There's 1, 2, 3, 4. So A equals 4. That carbon has no lone pairs, so L is 0. Question number 4, do we have a pi bond next door? No. and we don't even have any lone pairs. So P is not equal to 1, P is equal to 0, and H equals A plus L minus P, that's 4, and that's the number of hybrid orbitals we need, and that means we need to be sp3 hybridized. So this is sp3. Now, I'm not going to look up at the table because we really did it in the previous question. We saw that when we have an sp3 hybridized atom and A equals 4, that is going to give us a bond angle of approximately 109.5, and the geometry is going to be tetrahedral. Now again, I'm going to take a shortcut. This carbon by symmetry is the same. So this is also going to be sp3 109.5, or very close to it, and tetrahedral. Now that leaves us to this oxygen. This oxygen is indeed attached to more than one atom. There are 2 of them. So we've cleared the first question, and A equals 2. This oxygen has 2 lone pairs. There are no pi bonds in this molecule, so question 4 does not apply. So P equals 0, H equals A plus L minus P equals 4. We need 4 hybrids, therefore that oxygen is sp3 hybridized. And the oxygen, we saw this in the previous question, when we have an oxygen that's sp3 hybridized with 2 attached atoms, approximately 109.5 is our bond angle, and our geometry is bent. Okay, fantastic. That's problem 2. Problem 2 was quick. Let's go on to problem 3. Okay, this molecule is just a little bit bigger. We have 3. I'm sorry, I'm circling 4 and I'm saying 3. We have 4 second row elements. So let's go ahead and start with this particular carbon. This carbon is attached to 3 other atoms, so it certainly clears the first question. Number of attached atoms equals 3. Lone pairs, there are none on that structure. Now this fourth question is going to be kind of interesting. Is it and I've just written pi bond for question 4. If you go back, tell you what, let's do that. If you go to our questions, the statement is it attached to a pi bond? Okay, so now let's move forward back to our question. This carbon is not attached to a pi bond, it's actually involved. It's part of the pi bond. So technically, this is not attached to a pi bond. And furthermore, it doesn't have any lone pairs. But it's not attached to a pi bond, has no lone pairs, so P equals 0. We're going to have to make this distinction in later questions. So it's good to be aware that it's not just pi bond, it's a particular relationship. Okay, let's calculate H. H is A, that's 3, plus L, 0, minus 0 equals 3. Okay, we got a different number here. So if we have 3 hybrids, it's sp2 hybridized. Well, that's a new value. Let's take note of our attached atoms, that's 3, and sp2, and let's go to our table and figure out what that combination gives us. So our hybridization is sp2, and our attached atoms is 3. So we are going to have, for that carbon, 120 degrees is the bond angle, and trigonal planar as the geometry. So 120 and trigonal planar. That carbon is flat. Carbons that are parts of double bonds are flat. Now this next carbon, this next second row element, is going to be pretty similar. If we look, the carbon is attached to more than one atom. Here's 1, 2, 3. So A equals 3. There are no lone pairs. Again, this carbon is part of a double bond. It's not attached to a pi bond. And it doesn't have any lone pairs anywhere. So P, 0. And we're going to kind of get in the same number as the previous one. 3 plus 0 minus 0 is 3. This is also going to be sp2. Now, sp2 with 3 attached atoms, we've seen that before, sp2 and 3 attached atoms. And what we saw on the table was 120 degrees and trigonal planar. Great. Okay, now let's do our next carbon. We'll put it up here in the upper right. That carbon is attached to many atoms, four different atoms. And it has no lone pairs. Now, this carbon is next to a double bond. There's a double bond, then a bond, and then our atom. It is next to a double bond, but it doesn't have any lone pairs. So question 4 doesn't directly apply, and so P does remain 0, but at least we did have a double bond. Now, so H, we'd say H is A, that's 4, plus L, 0, minus 0 is 4. So we need 4 hybrids. 4 puts us back over here. That's sp3. I'm not going to write this whole one out or go back to the table because we've seen this. When A is 4 and it's sp3, we know that we're going to be 109.5 and tetrahedral. All right, finally, a little longer question. Let's go down to the bottom right and let's get this nitrogen. This nitrogen is attached to multiple atoms. 1, 2, 3. A equals 3. L, it does have a lone pair. Now, what do we do for this next question? Question number 4. So, is it next to a pi bond and does it have a lone pair? Well, it does have a lone pair, absolutely. But now, look, we're not next to the pi bond. The pi bond is not right next to the nitrogen. It's right next to that carbon. So that nitrogen is just one atom removed. Doesn't matter. It is not an attached pi bond. So P for this is going to be equal 0. It didn't fit both criteria, being next to a pi bond and having a lone pair. So let's tally up H. H is A, which is 3 plus 1 for the lone pair minus 0, and that gives us 4. We know if it's 4, it's got to be sp3. Now, this is a new combination, sp3 with 3 attached atoms. Let's go back to that table. So here we are, sp3 hybridized atom with 3 attached atoms. That's 109.5, and that's trigonal pyramidal. So let's fill up our page. This is 109.5, and again, it's nitrogen with a lone pair. It's not exactly 109.5. It's probably closer to 107, but hey, for an organic chemist, 109.5 and 107 are about the same number. So that's 109.5, and we want a trigonal pyramidal. Spelling. Spelling in a video, it's a challenge. Pyramidal. Okay, good. Okay, so great. That's question number 3. Oh boy, question number 4 is going to be a little interesting. So we have 4 second row elements. These 2 carbons are identical by symmetry, so we'll only do one of those. Okay, so let's start with this carbon on the lower left. That carbon certainly has more than one attached atom. It has 1, 2, 3, 4 attached atoms. So A equals 4. It doesn't have any lone pairs, so L equals 0. It actually does have a pi bond next door. That carbon is attached to a pi bond, but it doesn't have any lone pairs. So P is still equal to 0. Okay, let's solve for H, or determine H. It's A plus L minus P. That's 4. If we need 4 hybrids, we are sp3 hybridized. Now, we've seen this combination before. sp3 hybridized with 4 attached atoms. If we went back to the table right now, we would see that has a bond angle of approximately 109.5, and its geometry is tetrahedral. And of course, that assignment also holds up for that carbon on that other methyl group on the other side of the molecule. Okay, let's get this carbon in now. This carbon is attached to 1, 2, 3 atoms. Great. A equals 3. It doesn't have any lone pairs, so L equals 0. It is not next to a double bond. It's actually part of a pi bond, and that means it doesn't count. Didn't have any lone pairs anyway, but P is equal to 0. So we calculate H. H is 3 plus L minus P. H, as I already said, H is going to be equal to 3. H equals 3, we need sp2 hybridization. I think we've already seen this before, but let's go back. So just note A equals 3 and sp2 hybridized. Let's see, sp2 hybridized, A equals 3. This is going to be 120 trigonal planar. Okay, I'm glad we went back. So this is going to be 120 degrees and trigonal planar. Now I promised something at least a little bit interesting, and here's this oxygen. Now this oxygen is only attached to one other atom. And you might say, hey, but it has 2 bonds to an atom. I don't care. It's only attached to one other atom. That's one attached atom. So technically, we fail at the first step. This oxygen, properly speaking, doesn't have a hybridization. You could criticize that statement if you wanted to. I'm sure somebody will. That's okay. It's a valid comment. So this only has one attached atom. Even though atoms only might have one attached atom, it's still pretty common for people to talk about hybridization. And you might say that violates rule. It kind of does. But I said hybridization can be a controversial topic. So this atom, we're going to go ahead and assign a hybridization. So this oxygen is attached to one atom. So how would this work? So A equals 1, fine. That oxygen has 2 lone pairs. It's not next to a pi bond, it's part of a pi bond. So P is going to be equal to 0. So H equals A, that's 1, plus L, that's 2, minus 0, that is 3. So here we have attached atoms, 1, and we need 3 hybrids. I'm getting ahead of myself. We need 3 hybrids. That's sp2. Now, sp2 and 1 attached atom, let's see what we get when we go to the table. Okay, here we are in the table. We said it's sp2 and 1 attached. Oh, okay, there's no column for 1 attached atom. There is no bond angle. There is no geometry. Now, all sp2 atoms have bond angles of 120. So what can we do with this bond angle of 120? It does totally make sense here. We could at least say that the distance of separation, I didn't really want to make that a mark, the distance of separation around the hybrids, these 3 hybrid orbitals, is about a 120 degree angle. I keep calling bond angle. There's no bonds there. It's just lone pairs. But these are separated by about 120 degrees. So, yes, you can take atoms that violate this first rule. You can do the formula, figure out H, determine a hybridization, and even think about how, if these lone pairs were bonds, what would be the angle of separation. But technically, this oxygen has no geometry and no bond angle. So determining the hybridization is sort of a pointless effort. But you can do it. Okay, great. Let's go to problem number 5. It's a little bit smaller molecule. We just have 2 second row elements. This carbon will be fairly quick. It's attached to a lot of atoms. There's 1, 2, 3, 4. So A equals 4. We're now on question 3, number of lone pairs. That carbon has no lone pairs. We don't have any pi bonds around, so question 4 doesn't apply. So P is equal to 0. H equals 4 plus lone pairs. 0 minus P is 0. We've been here before. That's going to be sp3. Let's not even look it up. We have 4 attached atoms, and sp3, seen it many times before, approximately a bond angle of 109.5, and the geometry is tetrahedral. Now, let's look at the fluorine. This fluorine, like that previous oxygen, the fluorine is only attached to one other atom. So technically, it fails our first test. Let's go ahead and go through the steps, but some people would say, you're wasting your time. That fluorine, hybridization, whatever it is, if it is, it doesn't matter. But, so we have fluorine. It's attached to one other atom, that carbon. The fluorine has, I wrote F. I want L. I'm on step 3, so we're assigning L. The number of lone pairs is 3. It is doesn't have a double bond in the molecule, so P is 0. H equals A, that's 1, plus lone pairs, that's 3, minus 0 equals 4. And so if we get 4, we would say that that fluorine is sp3 hybridized. And you could even go further and say, since those hybrids are separated by, or since it's sp3 hybridized, the angle of separation between those lone pairs is in the ballpark of 109.5. But you can't call that a bond angle because there aren't bonds that are being separated. And you also can't call it as having a geometry. But you could make a statement and say, I think it's about sp3 hybridized. Okay, so that's that question. Let's go to question number 6. Okay, question number 6 has 4 atoms we have to focus on. So let's get to work. Here's this carbon. This carbon is attached to multiple atoms. It's attached to a carbon on the right and a hydrogen on the left. So A equals 2. It has no lone pairs. Carbon typically doesn't have lone pairs. And it's part of a pi bond, but it's not next to a pi bond. So we don't have to worry about that. P equals 0. H, we've seen the equation many times. A plus L minus P. That gives us 2. And then that means we need 2. This is sp hybridized. Okay, this is a hybridization we haven't seen yet before. So we know what the hybridization is. It's sp2 and A equals 2. Let's now go back to our table. So hybridization of sp, attached atoms is 2. This is going to have a bond angle of 180. Whoa, whoops. That is a mistake. That should not be bent. That's crazy talk. That should be linear. Whoops. Okay, I'm glad we caught that. I'll have to put a note on that first slide when we see it. But that is linear. And, okay, so let's remember that. sp with 2 attached atoms, 180 degrees, and that is linear. Okay. So we are going to have a bond angle of 180 degrees, and that geometry, try again, is linear. Okay, let's look at this next carbon. This carbon, again, this next carbon is indeed attached to more than one atom. It's attached to 2. So A equals 2. No lone pairs. It's part of a double bond, but not next to a double bond. Plus, it doesn't have lone pairs. P is 0. H, if we add everything up, A plus L minus P, that gives us 2. Once again, sp hybridization. I don't want to go back to that slide now because it has that typo. So we have sp hybridization, and A is 2. That's going to give us the same answer as before, 180, and it's linear. Great. Okay, let's do this next carbon. Little pen trouble. We'll go to the upper right. This carbon is attached to 1, 2, 3, 4 atoms. It's a carbon, so lone pairs are uncommon. Now, this is interesting. So this carbon, it is next to a pi bond. It's a triple bond. It's actually next to 2 pi bonds. But it's next to a pi bond, but it doesn't have any lone pairs. So this fourth rule doesn't really apply. So P is not equal to 1. P is equal to 0. I promise we're going to see this rule apply. Okay, H is A plus L minus P. That's 4. That gives us, if we look over to the left, sp3. And we've seen it a number of times. That's going to be 109 approximately, and tetrahedral. Okay, finally, let's take care of this oxygen. This oxygen is attached to 2 other atoms. It does have 2 lone pairs. Now for P, it has lone pairs, but it's too far away from, it's not attached to the double bond atoms. It's one too far away. So P is still equal to 0. H equals A plus L minus 0. That's 4. That gets us to sp3 hybridized. And we've seen it before. When it's sp3 hybridized and 2 attached atoms, we get 109.5, and there's that bent geometry I was looking for. Okay, but again, that table is incorrect. These are linear. Okay, good. Let's go on to problem number 7. Oh my goodness, what am I thinking? This is a huge molecule. We're not going to do all these. Okay, so I want to do the oxygen because that's kind of a key one here. And let's do, maybe 2 of the carbons. But once we do this carbon, we will have the answer for all these carbons. In fact, all the carbons are the same. Spoiler alert. Okay, so let's go over here. And for this particular carbon, we are attached to 1, 2, 3 atoms. A equals 3. No lone pairs, as usual, on carbon. This carbon, it's part of a pi bond. It technically is next to a pi bond, but if you're part of a pi bond, this rule doesn't apply. So P is 0. It doesn't have a lone pair anyway, but it's this is where this rule gets a little finicky. But it technically is carbon doesn't fit the rule. So H, how many hybrids do we need? That's A plus L minus P is 3. This is an sp2 hybridized atom. I think we've seen an example of this, but just in case, let's go back to the table. We have sp2, A equals 3. Let's go back. Here we are, sp2, 3 attached atoms. This is trigonal planar. So 120 degrees and trigonal planar. Fantastic. Now we're going to do this carbon as well. This is going to be quick. So this carbon also is attached to 3 atoms. Also has no lone pairs. Therefore, P again is going to be 0. If we go through the calculation of H, it's going to be 3 plus 0 minus 0. That's 3. It's also going to be sp2, also 120, and also trigonal planar. And in fact, every carbon in here fits the same deal. Every one of these carbons, sp2, every one of those carbons has a 120 degree bond angle approximately, and every one of them is trigonal planar. Okay, now that leaves this oxygen. And this oxygen, it does at least have 2 attached atoms, so we can talk about it properly. A equals 2. It does have 2 lone pairs, as oxygen often does. Now, here we go. Question number 4. Is it attached to a pi bond? That oxygen is attached to atoms in a pi bond. Yes, it is. Does it have more than 1 lone pair? Yes, it does. What do you know? P equals 1. Finally, we saw an example where this plays out. And I will say, this is not the norm. This rule doesn't typically apply, but in some cases it does. So this, how many hybrids do we need for this oxygen? Well, this is A, that's 2, plus the number of lone pairs, that's 2, minus P, so this is 3. Well, if we need 3 hybrids, then this is going to be an sp2 hybridized atom. So let's take a look at this. We have sp2 and 2 attached atoms. Let's see, sp2, 2 attached atoms. This is a new one that we haven't seen before. This is going to have a 120 degree bond angle, and it's bent. So 120 degrees approximately, and bent. Okay, great. That is question number 7. Okay, let's finish things up with this molecule. We have 4 second row elements. The nitrogens are the same, so we'll only have to assign 3. So let's start with a carbon, because it's the least interesting of the 3. So that carbon is attached to 1, 2, 3 atoms. A equals 3. There are no lone pairs. Since there are no lone pairs, we know P is going to be 0. It's also not next to a double bond. So when we calculate H is going to be 3 plus 0 minus 0. That gives us a total of 3. This is an sp2 hybridized carbon. It has, if we look this up in the table, sp2 and A equals 3. we would find that this has a approximately 120-degree bond angle, and it is trigonal planar. Okay, fantastic. Let's do a nitrogen. Okay, this nitrogen is attached to 1, 2, 3 atoms. Looking good. It has a lone pair. And now, question number 4. Is it attached to a pi bond? Well, yes, it is. There's the pi bond. It's right next to the nitrogen. So it has a pi bond and it has a lone pair. So P in this case equals 1. So H equals A, that's 3, plus L, that's 1, minus P, that's 1. And we get 3 for H, which is the number of hybrids we need. So this is an sp2 hybridized nitrogen. Now, I don't know if we've seen this before. Oh, well, we've, yeah, we have. Yeah, we have. So, but let's go to the table anyway. sp2 with 3 attached atoms. Here we are, sp2 with 3 attached atoms. This has a 120-degree bond angle, and it's trigonal planar. Oops, got to change to the pen. 120 degrees and trigonal planar. Fantastic. Okay, the other nitrogen, we get the same answer for that. So let's look at this oxygen. Whoops, this oxygen is not attached to more than one atom. It's only attached to one atom. Therefore, that oxygen technically doesn't have a hybridization. We can go ahead and assign it anyway, but there's no reason to assign hybridization because that's what we use to assign things like bond angles and geometries. And this doesn't have a bond angle or geometry. However, if we were to continue, we'd say it's attached to one atom. It does indeed have 2 lone pairs. It's not next to a pi bond. It's part of a pi bond. So P equals 0. H equals A plus L minus P. That gives us 3. This is going to be an sp. We would predict an sp2 hybridized oxygen, but there's no reason to look it up on the table because we won't find anything that has one attached atom in the table. So that is how we assign these hybridization and bond angles and geometries to second row elements. And I'd say the one real surprise in here is use of this additional rule to try to accommodate the idea of resonance. Now, if you never encounter resonance, your instructor may not care about this rule and may actually want you to completely ignore that, which will give you a different answer. I would say the answer is wrong, but again, follow the lead of your instructor. I hope you found this video helpful for learning about hybridization. Please subscribe, give a like, or leave a question or comment. Thank you for watching, and remember that links to these problem sets are in the video description. Take care.